Okay, so we're going to run through the P series. The P series, it's another integral test. If the series n equal 1 to infinity of 1 over n to the p, this is why we call it the P series, where p is a number, okay? This series converges if p is greater than 1 and diverges if p is less than or equal to 1, okay? So it converges for p greater than 1, and it diverges for p less than or equal to 1. All right, pretty simple to understand. Let's go through a proof of the P series. So I'm going to put proof in quotes here just because it's not exactly formal, but it'll get the job done. So here we go. We're going to use the integral test to prove this. So the integral test, I need to come up with a function f of x equals 1 over x to the p. Okay, this is true for x greater than or equal to 1, right? Okay. So what are we going to do? We need to show that f is continuous. F is continuous on 1 to infinity. Why do we know that? It's only discontinuous at 0. The only place that I can't do something is if I divide by 0, like x to the p equal to 0 in the denominator, that means x equals 0 there. So I can't have dividing by 0. Okay. Also, f is positive on 1 to infinity. Why? Well, since x is greater than or equal to 1, what does that mean? Okay, and 1 is greater than 0. That means 1 over x, okay, is less than 1 over 1, less than or equal to, which those are all positive, okay? What trick did I just use here? Well, and then if I raise it to the p, then this is going to be 1 over x to the p, and that's still positive, right? Why does this work? If I take a number, so any numbers where a is less than or equal to b, like this, then the reciprocal of those numbers, I just flip it around, okay? Just like this. Why does that work if you think about it? Like 2 is less than or equal to 3, but and those are both greater than 0. But if you think about it, 1/3 is less than or equal to 1/2, okay? So the bigger the number is, when I do the reciprocal of that number, the smaller it is. So we're just flopping around. So we're using this inequality. This inequality is going to be very helpful for you. Okay, so make sure you know that inequality there. Okay, f is decreasing on 1 to infinity. How do I know that it's decreasing? Well, f prime is equal to, well, what's the derivative of x to the negative p? That's what that equals, right? That's negative p times x to the negative p minus 1. So this negative p here, that's a negative number times something that's positive, that for sure is going to be negative, okay? So this is true, okay? So since p is greater than 1 and x is greater than or equal to 1, that's going to be true, okay? So it's decreasing on those values. If P was greater, then what would be going on here? Well, the exponent would then flip to the numerator and we would no longer be an increasing function, okay? Or I'm sorry, we'd no longer be decreasing. So you want like something, I'm sorry, never mind, scratch that. This piece right here, this is negative, which makes this whole piece here negative. And then we've got x greater than or equal to 1. Okay? All right. So now we've shown a function. We've got its continuous, positive, decreasing. We're ready to use the integral test. Okay? How's the integral test work? It's the integral from 1 to infinity, 1 over x to the p dx. Okay? When I integrate this, I get x to the 1 minus p over 1 minus p, integral from 1 to infinity. Well, we can't plug infinity, but we can take the limit, right? So if you're having trouble with this, this is equal to x to the negative p, add 1 to it. When I integrate, I add 1 to it, and then I divide by it. That's where that came from, okay? So limit as, let's say, b goes to infinity of x to the 1 minus p over 1 minus p b, and then 1. This is a limit that we talked about earlier in the course. This limit converges, okay? This limit converges to 1 over 1 minus p for p greater than 1, okay? For p greater than 1, all right? And it diverges for p less than or equal to 1, okay? And diverges for p less than or equal to 1. So what does that tell me? Then by the integral test, since Fn equals An and F is continuous, positive, and decreasing on x greater than or equal to 1, then the series n equal 1 to infinity, 1 over n to the p, converges if p is greater than 1, and diverges if p is less than or equal to 1. Those are my two options, okay? So that is the p series for you. All right. If I have a series and it's 1 over n to some power, then if p is greater than 1, converges automatically. All right, so let's work through an example, and you're going to see how easy it is to use the p series. P series is like number one go-to. Okay, very important. So determine if the given series converges or diverges. Okay. All right. Series n equal 1 to infinity, 1 over n squared. Well, let's show you how easy the p-series is to use. Since the series n equal 1 to infinity, 1 over n squared is a p-series with p equal to 2. That's how I want you to write your solution. Then the series converges since p greater than 1. Okay? And that's it. That's all there is to it. All right? Now, if I go back to that problem that I did earlier in the integral test section, I had n equal to 2 to infinity of 1 over n ln n. This is not a p-series. So I can't use the p-series test. This natural log thing is messing us up, okay? So that makes it where it's not a p-series. All right, so we'll talk about comparison tests soon, but for now, that's all we can do is we have to use that integral test there, which is a booger to use, but you can do it. Now, if I use the integral test on this series right here, I mean, I could still definitely get the answer. And look, we know because the series converges, the integral is going to converge, so why not just do it, right? So 1 over x squared dx. 1 over x squared is a function that looks like this. For x greater than or equal to 1, this thing is positive, decreasing, and also continuous. So, you know, I'm just doing some hand waving here just to show you, you know, that I can use the integral test. But when I integrate this, I'm going to get, let's see, x to the negative 2, add 1 to that's negative 1, divide by it. So I get negative 1 over x to the 1, limit as b goes to infinity of 1 to b. So this gets me what? This gets me negative 1 over b plus 1 over 1. And a limit as b goes to infinity. This goes to 0 plus 1. So my answer is 1 here. So this area, the integral here, is equal to 1. But if I added this up 1 to infinity of 1 over n squared, which is a pretty cool trick to do this, very few sums we actually know the exact answer to. But this is one that we do know the exact answer to, and I'm not sure if we're going to talk about in this class how to find this exact answer. But this is something that you would find in a more advanced calculus setting, either your junior or senior year, depending on when you take this. And so you can see clearly, you know, this is like 1.645-ish, okay? That is clearly not equal to the area 1 here. So just because, once again, just because the integral converges, the improper integral converges to a number, that doesn't mean that that series converges to the same number that it adds to that. In fact, it's very unlikely for that to occur, okay? So what to walk away with is we're not figuring out, when we're doing these problems, we're not trying to figure out what this thing adds up to. The only thing we're trying to figure out is, does it converge to something or does it diverge? Okay, so the goal here isn't to figure out what it adds to. It's cool that we know, you know, that it adds to this thing right here. The goal is just to figure out, do we converge to a number, or does this series not get small enough quick enough and it diverges? Okay, so that's the overarching idea of what's going on there for P-series. All right, guys.